Chapter 3, Internal Energy and Enthalpy. Section 3.1, U and H depend on PVT. The internal energy and enthalpy of a system depend on the pressure, volume, and temperature of the system. For a fixed amount of pure substance, out of pressure, volume, and temperature, there are only two independent variables. For ideal gas, because PV equals RT, then we can easily determine temperature given PV, or determine P given VT, or determine V given PT. For real gas, there are also only two independent variables out of PVT. If we look at the Reynolds equation, you can see pressure depends on volume and temperature. And also, if you want to determine the volume, we just need to know the pressure and temperature of this Reynolds gas. For liquids and solids, it's not obvious, but still, out of PVT, there are only two independent variables. It's just the equations that connect PVT are much more complex for liquids and solids. Now let's look at three equations that shows how PVT depends on each other. dV is delta V over delta T times dt plus delta V over delta P times dP. Pay attention to the subscripts over here. This means pressure is held constant. Over here, temperature is held constant. So we can examine this equation. When pressure is constant, dP is 0. When pressure is constant, we simply have dV is equal to delta V over delta T times dt. That makes sense. What if temperature is constant? When temperature is constant, dt is 0. So dV is equal to delta V over delta P times dP. It also makes sense. Similarly, we can express dP in terms of dt and dV. We can express dt in terms of dP and dV. For solids and liquids, delta V over delta T under constant pressure condition and delta V over delta P under constant temperature condition are roughly proportional to the volume of the liquid or solid of interest. And therefore, we define two parameters, alpha and kappa, as follows. We say delta V over delta T under constant pressure condition is approximately alpha V. Alpha is roughly a constant for a liquid or solid within a moderate temperature range, a moderate pressure range. And similarly, we say delta V over delta P under constant temperature condition is equal to negative kappa V. This kappa is also roughly a constant within a moderate temperature range and a moderate pressure range. Again, it just shows you delta V over delta P is proportional to the volume of the liquid or solid. Why do we need a negative sign here? It's just because when a liquid or solid undergoes a higher pressure, its volume decreases. So on the left hand side, we have delta V over delta P under constant temperature condition, and it's always negative. So by having this negative sign here, we can ensure the value of kappa is always positive. That's just for convenience. It's just because if you want to tabulate the values of kappa for 200 different substances, it's too tedious to just simply write this negative sign in front of every single value. Now kappa is always positive by having this definition instead. Alpha is the isobaric thermal expansion coefficient. Well, it's denoted by beta in some other physical chemistry textbooks, but UPAC use alpha. ACS officially use alpha, but occasionally use beta, unfortunately. And kappa is the isothermal compressibility. This is a little too long. Isobaric thermal expansion coefficient alpha. So sometimes we'll just say thermal expansion coefficient. And when we mention kappa, usually we just say compressibility, and that indicates as a thermal compressibility. Alpha is 1 over V times delta V over delta T. Under constant pressure condition, kappa is negative 1 over V times delta V over delta P under constant temperature condition. Kappa is always positive, alpha is almost always positive, except for water at 4 degrees Celsius. The physical meaning of alpha is the temperature dependence of the relative change of volume. Well, why did I say relative change of volume? Because we have delta V over V. Delta V over V is the relative change of volume. Alright, so really we are looking at delta V over V and then divided by delta T. The physical meaning of negative kappa is the pressure dependence of the relative change of volume. The SI units of alpha and kappa are Kelvin to the power of negative 1 and Pascal to the power of negative 1. Well, we can just look at the formula here. The unit of V cancels the unit of V, so really we have 1 over Kelvin here. In the expression of kappa, the unit of V cancels the unit of V, and then it's just 1 over the unit of pressure. So the SI unit for kappa is Pascal to the power of negative 1. The values of alpha and kappa of liquids and solids are approximately constant within a moderate temperature range or pressure range, sometimes even within a wide temperature and pressure range. So they can be treated as constant. And if alpha and kappa are constant, we can approximately say alpha is roughly delta V over V and then divided by delta T. Again, on top we have the relative change of the volume. On the bottom we have just the change of temperature. If we look at kappa, on top we have delta V over V. That's the relative change of the volume. On the bottom, that's the change of pressure. Just don't forget about this negative sign for kappa, and don't forget about the conditions. Alpha is determined when pressure is held constant. Kappa is determined when temperature is held constant. For an ideal gas, alpha is simply 1 over the temperature of the gas, and kappa is 1 over the pressure of the gas. We can easily derive this. Alpha is 1 over V times delta V over delta T under constant pressure condition. For an ideal gas, PV equals nRT. Delta V over delta T is simply nR over P. Now let's look at this. nR over PV, that's just nR over nRT. That's 1 over T. Right? Because PV equals nRT. Kappa is negative 1 over V times delta V over delta P. Now here we need to take the first derivative of volume with respect to pressure. Volume is nRT over P. So its first derivative is nRT over negative P squared. And we have negative 1 over V over here. You can see kappa is simply 1 over the pressure of the ideal gas. What about real gases? We know that real gases differ from ideal gases, but approximately you can still say alpha is approximately 1 over T, kappa is approximately 1 over P. Given the Van der equation, you can evaluate delta V over delta T analytically and also delta V over delta P analytically, and plug in those expressions to get the more accurate expression for alpha and kappa, but that's unnecessary unless you're really interested in doing a lot of tedious derivations. The values of alpha and kappa of gases are much larger than those of liquids and solids, simply because it's easier to change the volume of a gas than to change the volume of a liquid or a solid. Therefore, the alpha of a gas is much greater than the alpha of a liquid. And also, the alpha of a liquid is greater than the alpha of solid. We see the same trend for kappa. Kappa of a gas is much greater than the kappa of a liquid, which is much greater than kappa of a solid. Remember, it's possible to compress a gas with a high pressure, but it's much more difficult to compress a liquid with a high pressure or a solid. For liquids and solids, alpha and kappa are approximately constant within a wide temperature range and a wide pressure range. And also kappa and alpha are pretty small. The reason we introduce these two concepts, alpha and kappa, is to just make it easier to analyze how the internal energy, U, and enthalpy, H, of a liquid or solid depend on pressure, volume, and temperature. We'll see that later. For a fixed amount of substances, we have the three equations. They are all correct for du, the exact differential of internal energy. This is just because out of PVT there are only two independent variables, and U depends on the state of the system. So if you are given PV or VT or PT, somehow the value of U is determined. Therefore, you can say U is a function of TV, U is a function of TP, U is a function of PV. Either way is correct. If we say U is a function of TV, then du is delta U over delta T, constant volume, times dt, plus delta U over delta V, constant temperature, times dV. Also, you can express du in terms of dt and dp. You can express the expression of du in terms of dp and dv. But I would say forget about the last two equations. We will almost never use these two equations. We will almost always use the first equation. It's just because the first equation allows for more convenient derivations and numerical calculations. By looking at this, delta U over delta T under constant volume condition. Constant volume, that means work is zero, then delta U is simply dQ. dQ over dt under constant volume, that's simply C sub V. This part is simply the isochloric heat capacity. So we have a familiar thermodynamic function over here. And we can worry about this later. How does delta U depend on delta V? And actually for an ideal gas, this part is simply zero, because for an ideal gas, U only depends on temperature. Now let's look at this a little bit more closely. Delta U over delta V. What is this? Delta U over delta V under constant temperature condition. It's called internal pressure. Why is it called internal pressure? First, this U is internal energy, and it's delta internal energy over delta V, so it's called internal something. And also, if you look at the unit over here, this delta U is in joule, delta V is in cubic meter. So if you have 1 joule divided by 1 cubic meter, you get 1 Pascal. That's the SI unit for pressure. That's why this is called internal pressure. We can prove this delta U over delta V under constant temperature is simply T times delta P over delta T under constant volume minus P, later in chapter 5. But why do we need this? Well, it's just because it's very hard to measure how this internal energy changes with volume. It's a lot easier to measure how pressure changes with temperature under isochloric condition. So this is easy to measure. It's also easy to measure temperature and pressure, so it's easy to obtain the value of delta U over delta V experimentally by doing this indirect measurement on how delta P changes with delta T. And also, for ideal gas, we can easily derive this. For a real gas, we probably can derive this as well. Even for a liquid or a solid, if we can look up the values of alpha and kappa for the solid or liquid, we can compute delta P over delta T easily. So again, it's just for convenience. We want to do this. And also, I mean, it's just a lot easier for us to just, again, imagine, if we somehow have a gas, in a constant volume container, and then we change its temperature and then measure its pressure. It's just very easy to do this part. Unfortunately, we cannot prove this until chapter 5, so we're gonna just wait. Now let's just assume this equation is correct. And the du is simply CV dt, so this part is CV, and this part is delta U over delta V. We are replacing this delta U over delta V with this part, T times delta P over delta T minus P. For a fixed amount of substances, H depends on 2 out of these 3 variables, PVT. You can say enthalpy depends on temperature and pressure. You can say H depends on TV. You can say H depends on PV. So either way, you can write out a equation of the exact differential of enthalpy. So dH depends on dt and dP. dH depends on dt and dV. dH depends on dP and dV. Again, we almost always use one of the 3 equations, this one in the bold font. We almost always say, well, H depends on temperature and pressure for convenience. And dH is delta H over delta T under constant pressure condition times dt plus delta H over delta P under constant temperature condition times dP. So over here, you can imagine we have a isobaric process. When it's isobaric, we proved that dH is just dQp. So really, you're looking at dQ over dt on a constant pressure condition. Isn't that just heat capacity on a constant pressure condition, also called isobaric heat capacity over here? And delta H over delta P is more like complex, but we can prove this later in chapter 5. Delta H over delta P is simply volume minus temperature times delta V over delta T under constant pressure condition. Experimentally, it's easy to maintain a constant pressure condition, and then you can somehow heat up the substance and measure its volume change. And then we get this part. It's easy to measure temperature and volume, and then we get delta H over delta P for this substance. And for an ideal gas, delta H over delta P under constant temperature condition is anyway 0, because for an ideal gas, the internal energy and enthalpy only depend on temperature, and we are holding temperature constant here. This is just one line derivation of delta H over delta T on a constant pressure condition. H is just U plus PV, so delta H is just delta U over here plus delta PV. Delta PV is P delta V plus V delta P. Delta U is delta Q plus delta W, which is work. And because pressure is constant, so V delta P is just 0. And delta P is just negative P delta V, so these two also cancel. We just have delta Q left on top, so it's just Cp. It's the definition of heat capacity. Again, we can only prove this later in chapter 5 after the introduction of Helmholtz energy and Gibbs energy. So we're going to just use this equation without proving it yet, and we can see dH is Cp dt plus this expression times dP. Again, we do this because this is really easy to measure experimentally, and somehow it's really easy to derive delta V over delta T for an ideal gas. Even for a liquid or solid, somehow this delta V over delta T is related to this thermal expansion coefficient, alpha. It's convenient to express U as a function of temperature and volume. It's convenient to express H as a function of temperature and pressure. Again, it's just because du can be expressed as Cv dt plus this times dV, and dH can be expressed as Cp dt plus this expression times dP. The isochoric heat capacity and isobaric heat capacity can be easily measured. So these two can be measured. So are these two partial derivatives. This one, you can just hold the volume constant and measure the change of temperature and the change of pressure. Over here, you hold pressure constant and then measure the change of temperature and the change of volume. So we get everything then. For an ideal gas, we can even derive this easily. It's just because for an ideal gas, we know delta P over delta T is simply nR over V. So we just replace this with nR over V. We do some derivation, nRT over V, that's just pressure, it's going to be 0. And then we can derive this as well. Delta H over delta P is V minus T times delta V over delta T. For ideal gas, delta V over delta T is simply nR over P. Now we have V minus nRT over P, that's just 0 as well. So really for ideal gas, we just show that delta U over delta V is 0 if temperature is constant. Delta H over delta P is also 0 if temperature is constant. And remember, in thermodynamics, it's awfully important to have a subscript here, alright, and here. This is just because even for an ideal gas, if you ask me about delta U over delta V, but under constant pressure condition, I'm going to say that derivative is not 0. Delta H over delta P under constant volume condition is also non-zero. So it's awfully important for us to keep track of the subscripts. Again, the internal energy and the enthalpy of an ideal gas depend only on temperature. We will just further prove this for ideal gases. Delta U over delta P is also 0. Delta H over delta V is also 0 if the temperature is held constant. The derivation is very easy because first we have this two. We have delta U over delta V is 0. Delta H over delta P is 0 if the temperature is constant for ideal gas. And then we know this, H is U plus PV. And for ideal gas, PV is nRT. So if you really want to do delta U over delta P, you can just change this U to H minus PV. And you'll do delta H over delta P first, that's just 0. And then you'll do delta PV over delta P. It's also 0. Why is that? I mean, it's just a little confusing. So why is delta PV over delta P 0? Well, it's an ideal gas, right? So PV equals nRT, right? PV is equal to nRT. And temperature over here, look at the subscript. The temperature is held constant. Therefore, PV is a constant. And that's why this PV does not depend on pressure. Alright, so we get 0. And similarly, delta H over delta V, well, under constant temperature condition, H is 8U plus PV. And PV is a constant since we're holding temperature constant. So again, we get 0 over here. The internal energy and enthalpy of an ideal gas depend only on temperature. Another way to prove this in words is this. The potential energy of an ideal gas is always 0. Alright? So we don't have to worry about the potential energy. And energy is either potential energy that depends on the positions, or kinetic energy that depends on the motions of the particles. Alright? So if the temperature is constant, then the kinetic energy of the gas is also constant. That means, well, the internal energy is constant. If there's no temperature change, there's no internal energy change. And also, H is U plus PV, and PV equals nRT for an ideal gas. There's no change in nRT if temperature is constant. Therefore, in the end, if temperature is a constant, well, there's no change in internal energy. There's no change in enthalpy. Therefore, the internal energy and enthalpy of an ideal gas only depend on temperature. Now, what about real gas? Well, for a real gas, we'll just say approximately delta U over delta V is 0. Approximately delta H over delta P is 0 if the temperature is constant. And we can say the internal energy and the enthalpy of a real gas mostly depends on temperature. Well, they slightly depend on volume or pressure actually, but those dependence is much smaller than the temperature dependence. Alright, there are multiple models that we can use to describe a real gas. The most famous one is the Van der Waals equation, or the Van der Waals model. It's this. Let's review this. For ideal gas, P is just RT over molar volume. Why do we minus B? Well, B accounts for the finite size of the gas particles. B also has another meaning, which is the repulsion between the gas particles. A denotes the attraction between the gas particles. So we have two additional parameters. And also we can multiply the top and bottom by n over here, and also for this term we multiply the top and bottom by n squared. So we have this. Now using this Van der Waals equation, we can again evaluate delta U over delta V. It's just T times delta P over delta T minus P. How do we evaluate this? This is just the calculus. What's the first derivative of this term with respect to temperature? It's just nR over V minus NB. Just plug it in here. What about this term? This term does not depend on temperature at all, so ignore this. And therefore we have this expression. And P is this minus this. Plug in the expression of P here. You can see this term and this term cancel. So delta U over delta V is simply AN squared over V squared for this Van der Waals gas. Alright? So how does the internal energy depend on the volume when the temperature is constant? Well, it's just the attraction term in the Van der Waals equation. Actually, it is a flaw of the Van der Waals model, because supposedly when you change the volume, both attraction and repulsion should change. But over here it seems that we have only attraction in the expression here. Alright, so this is actually a flaw of the Van der Waals equation. But why do we still use Van der Waals equation? Actually, this is the simplest model for the real gas. It's just for convenience. We can have more complex models that can be used to describe real gases more accurately. And we can have a repulsion term over here. How does internal energy depend on volume? Actually, if you change the volume, you change the average distance between the gas particles. Supposedly, we need to have both attraction term and repulsion term here. Alright? Again, the Van der Waals equation is used for convenience because it's the simplest equation that can be used to describe a real gas. The Van der Waals parameter A for most gases are typically small because, you know, it's a gas. There's not much interaction between those gas particles. Alright? It's also possible to evaluate delta H over delta P on a constant temperature condition. It's a bit more difficult than this. There are many steps, but we can still prove this. Delta H over delta P is roughly NB minus 2AN over RT. So over here, it's nice that we have the attraction parameter. We also have the repulsion parameter. It does make more sense. And also, you can see these two may cancel, right? If you have the right temperature. If you just set NB is equal to 2AN RT, somehow you can solve this equation and get a temperature to cancel this two. Alright, so that means, well, delta H over delta P, well, it depends on two things: the repulsion terms and the attraction terms. Sometimes the repulsive term is predominant, and then this is positive. Sometimes the attraction term is predominant, and we have a negative dependence over here. For a liquid or solid, the variation of U with volume and the variation of H with pressure can be calculated given the values of alpha and kappa. Actually, that's why we introduced alpha and kappa in the first place. Again, alpha is the thermal expansion coefficient. Kappa is the compressibility. These two are the definitions of alpha and beta, okay, in the form of equations. Alpha is viewed as the relative volume change over the temperature change. Kappa is negative relative volume change over the pressure change. Using the reciprocal rule and the triple product rule, we can prove alpha over kappa is delta P over delta T on a constant volume condition. How do we do that? This is just purely calculus derivation. Alright, let's do it. Alpha over kappa is just, this is alpha, this is kappa, right? And then in calculus, we have learned this. The reciprocal of delta V over delta P is just delta P over delta V. You just flip this two. As long as these two derivatives have the same subscripts, exactly same subscripts, alright? So the temperature is constant here, the temperature is constant here. So this is called the reciprocal rule. And there's also a triple product rule. Alright, if you look at three variables, so you just write it down. V over T, and then P over V, and then T over P. So the product of these three derivatives should be -1. I think you can find the proof of this reciprocal rule and triple product rule on the wiki page of the triple product rule. Alright, you can see the derivation. But right now we'll just use this triple product rule. Alright, so again, if you have three variables and delta x over delta y times y over z times z over x, you have the product of three derivatives. It's just -1. There's a negative sign here, okay? And that's why we have negative delta v over delta t, delta p over delta v is equal to 1 over this. It's just because this times this times this is -1. Pay attention to the subscripts. So right here you see three different subscripts. So if you want to do v over t, make sure p is constant. When you do p over v, t is constant. Delta t over delta p, v is constant. And then finally we're going to use the reciprocal rule again. So make sure these two subscripts are the same. Then we can flip this. It's going to be delta p over delta t. So over here, alpha over kappa, that's just delta p over delta t on a constant volume condition. Now we have delta p over delta t. It's just alpha over kappa. This derivation is correct for all substances. So for a liquid or solid, we can still use this equation. We just need to look up the values of kappa and alpha for the liquid or solid. We plug those in, and then for a given temperature and pressure, plug in those values. We know how U depends on volume for liquid or solid on a constant temperature condition. Alright, what about delta H over delta P? So it's this. We can only prove this after chapter 5. Now we're going to just use this, and if you pay attention to this guy, delta V over delta T, it's simply V times alpha. It's just alpha is defined to be this derivative divided by V. So V times alpha is just this derivative. So we have this equation. Again, if you have the value of alpha for the liquid or solid of interest, it's a constant over a moderate temperature range and temperature pressure range. Plug it in. Plug in the temperature, volume, and then you get how the enthalpy of the liquid or solid depend on pressure. In summary, if we know the values of alpha and kappa, alpha here, somehow we can calculate how U depends on V and how H depends on P for a liquid or solid on a constant temperature condition. Now let's look at one numerical example. We'll calculate the internal energy change of 1 mole copper, a solid, at room temperature when its pressure changes from 1 bar to 2 bars. Here's the information about copper. We have the density, about 9 grams per milliliter. We have the value of kappa and alpha. For kappa, sometimes we use this reciprocal bar. Sometimes we use reciprocal Pascal. This is the SI unit. Pascal is the SI unit. 1 bar is just 100,000 pascals. Now let's look at this equation. This is how U depends on volume. It's T times alpha over kappa minus P. You should be able to derive this. The derivation, I think, is showing somewhere here. So this is a derivation for this is the derivation for the real gas. This is the derivation for the liquid and solid. Delta P over delta T is simply alpha over kappa. So we have the derivation of alpha over kappa right here. Alright, we just plug in numbers now. We have temperature, room temperature. We have the value of alpha and kappa, and we have the pressure. So I'm going to use bars as the unit for pressure and Kelvin as the unit for temperature. We get delta U over delta V over here. And now we need to know how much the volume changes. The temperature is constant, room temperature. The pressure changes. So I think the volume change should be negative. Alright, so we're going to use this equation for kappa. Kappa is negative 1 over V times delta V over delta P. And it's approximately delta V over delta P, so it's this much. And then we can get the relative volume change. Delta V over V is negative kappa times delta P. Well, it comes from this equation. And we just plug in numbers. We get this number without a unit for the relative change. Alright, this is negative. We can compute the volume of 1 mole copper. It's this much. 1 mole copper weighs 63.5 grams, and we have the density, and then we have the volume of 1 mole copper. Given 1 mole copper, its volume is this. Therefore, the change of the volume is the relative change times V. We get this much in cubic meter. When the temperature is constant, we have this equation. du is delta U over delta V times dV. We'll integrate both sides. Delta U over delta V is this many bars, 20,000 bars, somewhere here. This is huge, but volume change is so tiny that the product is very small. It's negative 0.0112 joule. This is very, very small. Numerical example 3.1.2. Calculate the internal energy change of 1 mole copper under 1 bar pressure when its temperature increases by Kelvin, 1 Kelvin. Alright, so we're given the density of copper. We have alpha and kappa, and we have the isochoric molar heat capacity, etc., etc. Now, first, we have the internal pressure over here. We computed this. It's about 20,000 bars. All right, and we can use this equation to compute the volume change, because we're holding pressure constant, so the volume depends on the temperature only, and this equation comes from the definition of alpha. Alright, alpha is actually delta V over delta T and then divided by volume. So if alpha is roughly a constant for a solid, alpha times delta T is roughly delta V over V. Alright, and we have the value of alpha, we have the temperature change. We multiply alpha and delta T, we get this relative change. We have the volume of 1 mole copper, 7 milliliters, and then we have delta V, also a very small change. Now, the internal energy is a state function, so that means we can compute delta U in 2 steps. It does not matter how we change the process, as long as the process connects the same initial state and the same final state. All right. Because U is a state function. So now we're gonna just look at how internal energy change with temperature here, and over here this is how internal energy changes with small volume. So when you see T here, that means T is held constant. Now we have 2 terms, 2 terms, 2 integrals. Over here this is CV. We have the value of CVM. Alright, so we're going to calculate this, and delta U over delta V, we have the value here. Alright, now what's CV? CV is CVM times the number of moles, alright, over here. And then times delta T, which is 1 Kelvin. Now let's look at the second integral. Delta U over delta V, it's this many pascals. Alright, I'm just using as a unit here. And times delta V, what's the volume change? Well, it's this much, very small. Now we have 2 terms. This is how internal energy depends on temperature. This is the internal energy change due to the temperature change. This is the internal energy change due to the volume change. Alright, so we have 2 numbers. We can see the internal energy depends much more on temperature than on the volume. Well, but we can also sum it up. We get this 24.44 joule. Alright, and this is the change in internal energy, alright, for this problem. It's a little complex. Alright, the internal energy change is decomposed into two parts. Over here we hold volume constant. Over here we hold temperature constant. The last numerical example in this section. This time we will calculate the enthalpy change of 1 mole copper. Room temperature will change the pressure. We have the density of copper. We have alpha and beta. So first, delta H over delta P is V minus T times delta V over delta T under constant pressure condition. This equation holds for all substances. Alright, this equation. We cannot prove this until chapter 5. So we'll just use this for all substances. And delta V over delta T is simply alpha times V based on the definition of alpha. Alright? It's also going from here to here, it's also exact for all substances. It's just for an ideal gas. This alpha is a variable. I think this alpha is actually 1 over temperature. For a solid and a liquid, this alpha is roughly constant. So we're going to do this. Copper is a solid, so alpha is going to be a constant. We look it up. We have the value of alpha here. We have T alpha, very small. 1 minus T alpha is close to 1. We also have the volume of 1 mole copper. We can do this calculation. Molar mass over density is molar volume. And then we have delta H over delta P. Roughly is 7 milliliters, or this much cubic meter. Now, when temperature is constant, dH is simply delta H over delta P times dP. Alright, over here. We can integrate both sides. We know this part is calculated already over here, and then we just need to integrate this delta H over delta P times dP, and this is a constant, roughly a constant. So over here the integral of dP is delta P. Delta P is just 2 minus 1, final minus initial. I'm using SI units because when I use SI units, I know 1 cubic meter times 1 Pascal is just 1 joule. Feel free to use liters, ATM, PSI. It's just a little bit more tedious to do unit conversions. So right now I just get 0.7 joule. We know the isobaric molar heat capacity of copper is about 24.4. You can look it up. When temperature increases by 1 Kelvin, the enthalpy of this copper increases this much. Again, when temperature changes by only 1 Kelvin. However, if you change the pressure from 1 bar to 2 bars, well, the enthalpy changes only by 0.7. Compare these two numbers, 24.7. So we're going to say enthalpy depends more on temperature than on pressure for copper. In general, both internal energy and enthalpy depend more on temperature than on pressure for solids and liquids. How about real gases? Well, still, internal energy and enthalpy depend much more on temperature than on the volume or pressure. What about ideal gases? Well, that's the extreme case. Internal energy and enthalpy of an ideal gas only depend on temperature. They do not depend on pressure or volume at all for the ideal gases.